Hello everyone. In this video, we are going to briefly discuss parallel data communications and signaling levels. So if you watched one of my previous video, I talked about the serial communications, synchronous and asynchronous, like SPI, like I square C, and then UART. So here I want to briefly talk about parallel ones, compare it with the serial ones, and then signaling levels. So some pictures and text are coming from our mechatronics textbook, as well as this top one is coming from Wikipedia. So bit parallel communication as opposed to bit serial communication is when, instead of sending the data bit by bit in a sequence like that, so starting with the first bit and then going all the way to the last bit, then you do all of them at the same time. So from your transmitter to your receiver, TX to RX, you're going to send maybe 1 byte at a time, or 2 bytes, or several bytes at a time, or so many bits at a time. So you do it with several wires or several channels. Okay, so this can definitely improve the speed, of course, because you're doing it all at the same time. Now, one example of that is, for instance, if you want to communicate between a PIC microcontroller and one LCD module, which is one of my future videos, but of course I do it with Arduino. This is one place that you basically communicate with parallel communication as opposed to serial communication. So you see that all of these informations here, RB1 to RB7, are going to here, and there are sometimes some extra wires in addition to data, which I'm going to talk about. But in general, you see that this communication can be done by it is done by a parallel communication. So as I said, a parallel communication can have other signals too. One of them is a clock signal that sometimes it does because it wants to control the speed of the flow of the data. The other one is one that controls the direction of the data flow, right? Which direction are they going, from device 1 to 2, 2 to 1? And many times there are several devices. It's not just between two devices. So you need to know which direction they are going. And another one, this terminology called handshaking signals. This is an interesting one. I wanted to just explain it. So handshaking is when two devices or programs or anything they are communicating, they use these signals to authenticate and coordinate. Like what? Like, for instance, the protocols they use for communications. At the beginning of their communication, they want to know what kind of protocols they are using for communications, what kind of bits they are using, right? Is there a parity bit or not? And what are the number of bits? What are the speeds, and so on? So before two devices start communicating, sometimes there are some wires called handshaking signals or wires that set up these initial protocols and standards. Otherwise, there will be not a successful communication. So sometimes you have some of those wires too, in addition to just the bits of the data. Okay, now there are a few formulas that I want to show you, very simple formulas that I want to show you, and then we briefly talk about what kind of devices are using it, what are the advantages and disadvantages of that, and then, as I said, we go to signal leveling or levels. So the first thing is, of course, the data transfer rate, or DTR, which is N times F, and F here is the clock frequency using which you are sending your data, and N is the number of parallel lines, right? So if you have 8 lines and each line is taking 1 bit, right? Then if your frequency is, I don't know, let's say 16 megahertz, then it is going to be 8 times 16 mega. And since it's bits, and this is 1/2, it is going to be bits per second, or BPS. Okay, so this is basically 128, right? Megabit per second. So that is the data transfer rate. The next one is called the propagation delay formula. So if you are sending a signal and the signal travels with the speed of v, and it travels over a distance of d, the time it takes to travel that, assuming that v is constant, is of course d over v. So if you start here at time of t naught, send the signal, the time that it is received on the other end is going to be t naught plus this delay time. Okay, nothing happens in no time. Everything needs some time, every signal. Even if the signal is traveling at the speed of light, right? Depend on whatever it is. It's not necessarily always a fiber optics or something, right? So the speed, this v, if you know it, what is the speed that the signals are going over what kind of length of wire, if it's a wired one, then there will be some delay. And if you're wondering what is this speed, so it is related to the speed of light, but not exactly. Many times this is somewhere around like, let's say 50, 60%, 60% of the speed of the light, right? Or smaller than that. For instance, if you look at the fiber optics, in fiber optics, it can go up to 2 times 10 to the 8, right? But if you're doing it in copper, then you're looking at something like, for instance, 1.8 to 2.25 times 10 to the 8. Okay, so this is for fiber optic. Now, of course, it's not a fixed number, but something like that. And this is in copper wires. So still, there is some delay, although it could be in microseconds or milliseconds or something, but it is something that should be considered. And that is very important in this next formula called the bit skew. Okay, this is the max delay minus the min delay in absolute value. What is that? Well, here you're sending these data in several lines. Sometimes these lines are going into different locations. The length of the wire for them is different. So one of them is shorter, one of them is a little bit longer, one of them could be longer, one of them could be very long. So this one is going to have some maximum delay time, and this one is going to have some minimum delay time. Not all of the information are reaching their targets at the very same time. So the difference between max and min delay is called the bit skew, and basically this should be limited, or you should have some way to recover the signals to make sure all of the data that you are processing belong to the exact same time. Okay, so the bit skew is another important factor when the length of the wires carrying the information, they're not all the same. So these are 3 important things that I wanted to tell you, and probably you know some of that. Now, what kind of devices use parallel communication, bit parallel communication? Well, there are a bunch of them. Here I just wrote some of them for you. So many of the computer buses, internal computer buses, they are using that. So here are a bunch of different standards for parallel communication. One of them is called Peripheral Component Interconnect, or PCI. Next one is called Accelerated Graphic Port, AGP. These two are mostly for graphic cards. Then we have Integrated Drive Electronics, or IDE, Serial Advanced Technology Attachment, or SATA. So these are some common things that you have in computers for connecting with the peripherals and for graphic cards and so on. In older printers, you use this centronic interface. In RAMs, especially dynamic RAM, random access memory, for basically data transfer to CPU and storage, they use parallel communications. Then we have A to D and D to C, correct? Analog to digital and digital to analog converters. That C stands for converter, and we use them a lot in control systems, and they typically use parallel communications, A to D and D to A, or ADC and DAC, for high-speed processing. And finally, for microcontroller interfaces and also FPGAs, FPGAs fill programmable gate arrays. And these are special, basically integrated circuits that are used a lot in machine learning and deep learning for their fast processing powers. And then any microcontroller unit or MCUs, they also use parallel communication for the speed of it. So as you may recognize, the biggest advantage of parallel communication is, of course, higher data transfer rate because you're doing several lines, several bits at the same time. Of course, higher speed means reduced transmission time, right? And then they are actually relatively simple implementations as long as your data transfer is mostly within short distance. And the reason for short distance is so that the delay is not significant and the bit skew is not very large. Okay, so when we come to disadvantages, one of the major things is distance limitations. We typically do not use them over long distances. Okay, we use them in shorter distances. Now, because they have more physical connections, they have a little bit higher cost and complexity. Now, mostly cost, really. And of course, the other thing is called signal interference and crosstalk, because you have several wires next to each other carrying signals. Their magnetic fields can interfere with each other. So you have to make sure that these signals are not affected by the neighboring signals, okay? So you have to pay attention to that part. But these are basic advantages, disadvantages of parallel processing. These are some relevant formulas for it. This is an example in real life. This is how it's different from serial one and some devices that are using it. As I said, my goal is not to go into depth of this because each one of them is like a can of worm. You open it, you have to talk about it. So I don't want to talk about FPGAs or SATA or all of these standards. I just want to briefly say what is parallel communication. The next thing is signal levelings. So we always get used to say that, hey, 0 or logical false means 0 volts and logical 1 or true means 5 volts. Well, not always. Depending on the kind of standard that we are using, different standards use different voltage levels to show a Boolean false and a Boolean true, okay? And the level of voltage they use to represent those is called signal leveling or levels, okay? So like what? For instance, in TTL, which stands for transistor to transistor logic, and CMOS, which is complementary metal oxide semiconductor, in these kind of standards, mostly it is like what we said. So 0 volt is typically used for 0 logic, and 5 volts, or if it's 3.3 like RPi, then you can use what? You can use logic 1. So for TTL and CMOS, you see that's very similar. Logic 0 is 0 to 0.8, here is 0 to 0.3. That range is considered 0. And then a range from 2 to 5 is typically considered logic 1. And basically from 0.7 VCC to VCC is considered logic 1. So for instance, if your VCC is 5, something like 3.5 to 5 is considered logic 1. And I mentioned that in one of my previous video, when I mentioned that in idle situation, some of these microprocessors and control systems, they use idle high as opposed to idle low, is because of the range that you have, okay, different ranges and so on. So I mentioned that. Now, between the TTL and CMOS, remember that TTL is basically the faster one, okay, but it is using more power, as you can see here, right? The ranges of the voltage. CMOS is more power efficient, of course, and its impedance, input impedance, is higher. So many of modern devices for parallel communication, they use CMOS level and standard as opposed to TTL because it is not using as much power. And there are two other standards that are very common. One of them is called recommended standard 232 or RS-232. Okay, so first of all, it is for serial communication. This one is not for parallel communication. This one is for serial communication. So this topic of signal leveling is actually separate from the previous topic, parallel processing, okay, parallel data communication. They are two different things, okay? So do not think that just because we talked about parallel, now anything that we talk about at this point is also necessarily a parallel one. Not really, okay? So you can see that the RS-32 is for serial communication and is for asynchronous one, like UART or something. It's typically used between computers and peripherals, such as modem, printer, and other things, other serial devices. And it is used typically in short distances, up to like 15 meters or so, okay? The data transfer of it is typically lower, so it's not super fast. Another thing about RS-232 is it's a single-ended signaling. What does that mean? It means the voltage levels are all defined relative to one common ground. Another thing about it is called the bipolar signaling. What does that mean? It means your voltage can go both positive and negative. If you look at CMOS and TTL, they are all always positive, bigger than or equal 0. But if you look at RS-32, you see that logic 0 for it is negative 12 volts to negative 3, and logic 1 is positive 3 to positive 12. So you see it can go negative, and that's why we call it bipolar signaling, okay? Yes? Now, RS-32, remember, in general, is just more than just setting up the voltage level for logical 0 and logical 1. RS-32 has a lot more. As I said, each one of them is a can of worms, so we can make probably a couple of lectures or more just to talk about RS-232, and that's not what I want to do, because this one actually has naming convention for signals, for pin assignments, for protocols, and so on, for data transfer. All of them are provided in RS-232, not just saying, hey, logic 0 is negative 12 to negative 3, logic 1 is positive 3 to positive 12. It's more than that. But what I want to focus right now mostly is what kind of voltage level they use for 0 and 1. So you have to pay attention to this kind of thing, right? When you are picking your power sources, you have to know which standard you're using for communication, so you pick the appropriate power source. And finally, we have the newer version that is called Recommended Standard 485 or RS-485. This is also for serial communication, but this can work for multi-point communication, meaning that several devices could be connected to the same bus, up to 32 devices. It is mostly used for line distance communication as opposed to the previous one, which was for short distance and for industrial applications. The wires, it can transfer up to 1200 meters. Remember, last one was only up to 15 meters. So in industrial environment, you use RS-485. And the data transfer rate is much higher, 10 megabit per second. Also, it is better in terms of noise immunity or resistance to noise, and not being, the interference of noise is much less in RS-485. So it is the common standard for many industries, but for simple applications, computers, simple microprocessors, you can use RS-232, and these are both for serial communications, okay? So these are both for serial communications. But again, my goal is not to go between serial and parallel. We are just talking about voltage level here. Now for 485, logic 0 is between negative 2 to negative 6. Logic 1 is between positive 2 to positive 6. So you see, this is also a bipolar one, but the range of voltage is a little bit, or it's about like half of RS-232. So I assume it is using less power as well. It's more power efficient as well. So hopefully this simple video was useful to you. You learned some basic things about signal leveling and parallel data communications. Thank you so much. I'll see you in the next lecture.